Hi folks, welcome back to Physics with Captain Rod. The purpose of this video is to discuss how to solve what are called second order homogeneous differential equations. And we're looking at a pair of them here, and we're going to discuss both examples here. We've got this animal here and this animal, and they're very close, but they do differ by one factor. You notice this minus sign and this plus sign. So first we're going to talk about this guy. Now, I think it's very important to understand the mathematical structure of these equations here. So in this equation, x and y are the variables. And y is a variable that depends on x. So we would say, all right, y is equal to some function of x. So y is called the y is called the dependent variable, x is called the independent variable. Now this equation is saying that whatever y is as a function, we need to be able to differentiate it twice, subtract it from itself, and get 0. Now I know there's a 4 there, but to within a multiple of 4, we need to be able to differentiate twice, subtract the function again, and get 0. And if we think about the types of functions that exhibit that behavior, there's only one type, and those are exponential functions. For example, if I take y equals e to the x, when you differentiate e to the x, you get e to the x. And when we differentiate e to the x again, we get another e to the x. Notice if I take y double prime, subtract y, I get 0. So exponential functions are functions that exhibit this type of behavior. All right, let's take a look at that other side here for a moment. All right, if we look over here now, all right, again, y is the dependent variable, x is the independent variable. So the solution of this equation is some function. And in this example, we need to be able to differentiate that function twice, add it to itself, or I should say add it to a multiple of itself, and get 0. And there's really only one type of function in the universe that exhibits that type of behavior, the trig functions, specifically sine and cosine. If we take a look at y equals sine x, or y equals cosine x, either one. If you differentiate a sine function, you get a cosine function. Or over here, if we differentiate a cosine function, we get, minus sine. And when we take another derivative, we now have minus sine x. Or on the right-hand side, if we take another derivative, we have minus cosine x. Notice that if I take y double prime and I add it to y prime, I get 0 in both cases. So the type of function that solves this type of equation are sinusoidal functions, sines and cosines. So I'm going to go back here. We're going to take a look at this. And again, from our discussion before, we know that exponential functions solve this, equations of this form. So I showed quite clearly that y equals e to the x is a type of function that solves equations that look similar to this. Now, what we don't know here, you see, in this example, I've got a 1 here, but for all we know, there could be a constant here. And I've got e to the 1x, but for all we know, there could be a constant in front of the x. So I'm going to write this y equals a e to the bx as kind of a generic function that I believe may solve this equation. Now what I'm going to do is I'm going to sub that in to this equation and try to get a solution out of it. Now in order to do that, I need the second derivative. So the first derivative here, let's see, when we differentiate an exponential, remember that the derivative of e to the u is e to the u du. So this function's derivative is going to be ab e to the bx. And then if we differentiate it again, we're going to get ab squared e to the bx. And again, this b is coming from the chain rule from differentiating this part of it. And again, this other b, same thing. Now when we take this and we sub it into this equation, this is going to read ab squared e to the bx. That's our y double prime here, minus 4 times y, but y, I believe, looks like a e to the bx equals 0. Now, this equation here can be factored. We can factor an a out of it. We can also factor an e to the bx out. And then we're left with b squared minus 4 equals 0. Now, Theorem of Algebra here, I've got 3 things. The product of 3 things equals 0. One possibility is the first one equals 0. This is a solution that is typically thrown out because if a is equal to 0 and I look at my solution here, I don't have a solution really. I have just y equals 0. And although that actually solves this equation, if I differentiate 0 twice I get 0, and if I put a 0 here I still get 0, it's not what we're looking for. That's called the trivial solution. So this we don't allow. E to the bx isn't 0 for any values of x. So the only thing left here is this, b squared minus 4 equals 0. And it's not too hard to show that the solutions of that are b equals plus or minus 2. Now, when I compare the functions y equals e to the 2x and y equals e to the minus 2x, and I'm going to pause this for just a moment. Okay, I'm back here. Had to answer my door here. Got to go back and kind of review for myself where I was at here. So let's see. We're solving this differential equation, assuming an exponential solution. Differentiated twice to get this, subbed this and this into our original equation. Okay. And out comes two values for b. Now, 1 plus 2, 1 minus 2. When we compare these two solutions, like if I put the plus 2x in for b, whoops, and to tell you the truth, this should still have an a in front of it here and here. ae to the 2x and ae to the minus 2x are in fact different functions. So because these are different functions, both of these solve this. So what we really have are two different solutions here. I'll say like y1 and y2. Now, they could in fact have different values of a here. So maybe I'm going to rewrite this and say that, maybe y1 here I'm going to call ae to the 2x, and then y2 I'm going to actually just change this to a c because it isn't necessarily the same constant as the first one here. So I'm going to call this ce to the minus 2x. Now when you have two different functions, both of which that solve the differential equation, it's quite easy to show that if this equation is what's called a linear equation, and most of the equations that we deal with will be linear, then the sum of the two also solves it. So I'm going to write here that y, I'm going to put a g for general, is equal to ae to the 2x plus ce to the minus 2x. And this is what's called the general solution of this equation. The constants a and c would be determined from initial conditions of the problem, which are not given here. All right, I'm going to talk about the one on the right now. So before I do that, I need to make myself a little bit of room. Take that work, shrink it down, move it over. All right. So we're going to take a look at this equation. Now, this one we're looking at here, we have second derivative of y plus 4y here. So now we're looking for a function that we can differentiate twice, add it to itself, and get 0. Sines and cosines are functions that exhibit that behavior. So one possible solution, all right, well maybe y equals sine x. But 1 sine x, or maybe 2 sine x, or 3 sine x, I'm going to go ahead and put a constant here for the fact that we could have a numerical constant to determine here. Could also be a numerical constant here. Another possible solution is a cosine function. So I'm going to put maybe a c cosine of dx. As you can see, I'm not real imaginative about where I get my constants. A, B, C, D, if I needed another one, E, F, G, and so forth. So these are two possible functions here that solve this equation. Now I'm going to take these one at a time. I'm going to take this guy. In order to sub this into this equation here, we're going to need the second derivative of y with respect to x. All right, so y prime, differentiating this function, is equal to ab cosine of bx. If we differentiate it again, right, now the derivative of cosine is minus sine, so now we're going to have minus ab squared sine of bx. And the reason that became a squared is because of the chain rule. If we differentiate that term, we're going to have times b. In fact, that's where this b came from as well. So now what we can do is we can sub this and this into our original equation. It's going to read minus ab squared sine of bx for this term, plus 4 times y, and y is equal to a sine bx, equals 0. This can now be factored. We can factor out an a and a sine of bx, and then we're left with minus b squared, whoops, looks like a d, minus b squared plus 4 equals 0. All right, so now what we have here is we have the product of three things equals 0. Well, this one we cannot allow. A cannot equal 0, because if it did, we wouldn't have a solution. This would just read y equals 0. Or actually, I should say we would have a solution, but that one's called the trivial solution. That's not what we're looking for. Sine of bx can equal 0, but only at very specific values of x. That's not the one we want either. The other solution is if b minus b squared plus 4 equals 0, or in other words, if b equals plus or minus 2. Now, let's talk about the different possible solutions here, the plus 2 and the minus 2. So if I write out y equals a sine of bx, and then imagine I got a second function, whoops, not bx, let me write 2x. And then let me look at another function, y equals, and for now I know I have an a here, I'm going to put maybe a prime, different possible constant, sine of minus 2x. These functions might look different, but they're not. They're basically the same function. And the reason is because the sine function is an example of an odd function. And remember, you know, that sine of 30 is positive 1/2. Sine of minus 30 is minus 1/2. And this is true for any angle theta. Sine theta and sine of minus theta are the same to within a minus sign. What that means here is basically, if I compare these two functions, I can choose a value for a prime, namely minus a, and then these are exactly the same functions. So, long story short, this is not two different solutions here. The minus 2 in this case does not yield a second independent solution like it did with the exponential function. So, our second solution comes from the cosine part. I'm going to get rid of this. So we've gone through all of this work, and what we have shown is that, let me write it down, I'm going to call y1 is equal to a sine of 2x solves this equation. It's very easy to show if I put a 2 on this guy right here. y2 equals c cosine 2x also solves it. Now, I skipped a bunch of steps here. Let me talk about what I skipped. If I take this function, differentiate it twice like I did here, sub this here and this here, and repeat the algebra process, you will get d equals plus or minus 2 out of this. And again, the minus 2 doesn't change anything. All right, you're getting the same solution because cosine of 2x and cosine of minus 2x are exactly the same solution. But the important thing here is that if you solve it for d, you get a 2. So here's two different functions that solve this equation. The sum of the two is called the general solution, just like it was before. I'll put y general here equals a sine 2x plus c cosine 2x is the general solution for this equation. So a and c in this example are constants that would need to be determined from initial conditions of the problem. And I think because this video is pushing 14 minutes here, I'll just save that for another video. I hope this video helps demonstrate how to solve these second order types of differential equations. Have a great day.